Hello, welcome to Group47's final demonstration. My name is Ezra and I am joined by my fellow group members Daniel and Jenna. Our project focuses on developing an alert bracelet to assist visually impaired children. The group conducted an interview with the parent of a visually impaired child. During this interview, it was found that young children with vision impairments can find it challenging in areas they aren't familiar with, as they can lose sight of their parent and become distressed. It was found that there exists a need for a device which can alert the parent when the child becomes distressed, or when the child goes out of the parent's surroundings. By providing a solution to this problem, the parent would be able to gain more freedom and the child can become more independent. The user would be a young child who has a visual impairment. This visual impairment limits the child's vision to 20 degrees, which means their peripheral vision is severely restricted. They require a reasonably priced device which could be used to alert their parent when they are lost and distressed. The device would ideally provide a method to send a discrete alert. Functional requirements include the development of a discrete solution which can be easily operated by a child. This would include a simple interface and a minimalistic user experience. The solution must be cheap and portable while also being low-powered. There must also be a way to alert the parent when the child becomes distressed, and the child should be able to request a distance measurement from the parent. To achieve these requirements, the following solution concept was produced. The solution would be in the form of a wearable wristband device for the child. This device would be capable of notifying the parent when the child becomes distressed. It would also be able to receive an alert when the child goes out of range of their parent. The child should be able to request their distance from the parent as well.
Our device can be represented in two functional blocks: the smartphone component running on an iOS device and the wristband with haptic capabilities. These two components communicate using the Bluetooth 4 low-energy protocol. Starting with the mechanical aspects of our design, the enclosure design was 3D printed and houses all electrical components. Initially, the circuit was to be placed on a printed circuit board. However, due to time constraints and acquirement issues, VeriBoard was used instead. The casing was designed to house the VeriBoard circuit with tabs on either side to attach a wrist strap. The PCB schematic is still available for future revisions of the device, and no modifications should be required to the mechanical drawings to house it. The constructed device fitted exactly into the casing as was designed. The power switch and push buttons pressing through the holes at each end can be seen in the first picture. The entire device is easily removed from the case via a door at one end, which allows for simple replacement of batteries or repair. The whole device is attached to the wrist via a hook and loop strap, which is adjustable and can suit any wrist size. Looking at the electrical design of the device, the electrical component consists of two major parts: the Bluetooth beacon, which is a prefabricated purchased device, and the circuitry required to drive the motor and communicate with the beacon. The diagram can be seen where the suppliers represent separate 3V 2032 coin cell batteries. One powers the Bluetooth module and the other the motor. Each have been decoupled, the module to provide protection and the motor to provide assistance with the startup current required for the motor. To protect the circuit, a flyback Schottky diode has been placed across the motor and a series 100 ohm resistor connecting the two battery grounds together. Finally, an N-channel MOSFET is used to perform the switching of the motor and allow for PWM. Following from the circuit schematic, the physical components required are 1. A Nordic Semiconductor NRF52 Bluetooth module. This is the deployable version of the development board which was used throughout our project. This is plugged into the dual inline female headers, allowing for the device to be removed and reprogrammed if required. The MOSFET used is an N-channel FDV303N, which was chosen due to the low drain source voltage required to energize the gate, making it appropriate for 3V low side drive circuits. The haptic motor is capable of being run from a 3V and a PWM signal, which allows for different types of haptic messages to be transmitted to the user.
We have modeled the interactions between the bracelet and mobile phone app using state machines. This enables us to formalize the intended behavior of the device and prevent any unexpected behaviors. This is the state machine for our firmware. Arrows show transitions. Arrows with labels on them show the inputs that are sent to a subsystem, such as button presses or Bluetooth signals. A diamond block indicates output to a user, which could be visual or haptic. Here, we see that the Bracelet firmware's task is to communicate with the child using haptic feedback and maintain a connection with the phone. It must transmit a distress signal to the phone if the child presses the button or goes too far away. This brings us to the mobile app that is used by the parent. The app's behavior is also modeled as a state machine. Let's unpack it by looking at what the app user would see.
To set up the device, the user first opens the application on their phone. While the device is turned off, the app shows that the phone is waiting to connect. The device is then turned on and the app shows that the device has been found. The user clicks start and the device and phone are connected. The child is now able to go and play with the peace of mind that if they become distressed, their parent can be easily alerted. The child has now lost track of their parent. They press the distress button to alert the parent and the wristband begins to vibrate, notifying the parent is on their way. The parent receives a notification on their phone saying "Come find me" when the child presses the distress button. The parent approaches the child and cancels the alert once they are close together. Later in the day, while the child is playing, they go far from the parent. The parent now receives an alert saying "Come find me" as the child is too far away. The wristband begins to vibrate, alerting the child that they have left their parents' surroundings.
We performed two quantitative tests. The first test is to validate our model for the relationship between signal strength and distance. The app has a feature that enables viewing the signal strength. Under line of sight conditions and keeping the relative orientations of the phone and bracelet constant, we vary the distance between the phone and the bracelet and measure the signal strength at 1 meter intervals. The RSSI measurements have an increasingly wide envelope after about 6 meters, making distance prediction imprecise. Based on this data, we made an engineering decision that if the RSSI is lower than -100 decibels after 10 samples of successive averaging, then the child is too far away from their parents and the device should send an alert. Our second test is on the way that the device's orientation affects the signal strength. We held the devices 1 meter apart and kept the phone steady. Then we rotated the bracelet 180 degrees at a time along each degree of freedom. As we expected, the signal strength is anisotropic, meaning that it depends on the orientation of the antennas. Finally, we tested to ensure that the bracelet would send a distance alert well before the Bluetooth connection was dropped. Our devices were still connected at about 25 meters, but the connection was lost as soon as line of sight was broken. This means that under some circumstances, the distance alert may not trigger before the connection drops out. Therefore, we will recommend that this device is only used under line of sight conditions, such as in a single room or a large open space. A questionnaire was issued to the potential user for this device. She is mainly concerned about what happens if the Bluetooth connection is lost. Our haptic scheme outputs one short periodic pulse if the connection is lost, but she is concerned that this might not convey enough urgency to the child. She is also concerned about the durability of the device during rough play.
Leading on from the feedback received, we have identified some limitations of our device which will also be addressed in our future work. The most significant being that RSSI is a poor estimator of distance and accuracy only decreases with more cluttered scenes and the breaking of line of sight. This may have been mitigated slightly with the inclusion of sensor fusion techniques. However, the processing and power requirements were too large for the device we chose to use. Additionally, the constructed device is not suited to an active child's lifestyle and may be easily broken. In future revisions, built with smaller scale components, a more sleek and waterproof enclosure may be designed to deal with the punishment a child may deliver to this device. Some final limitations include that of whether the child wishes to wear a wristband or some other form of wearable, and the limited functionality and platforms the mobile app is targeted at. With the time constraints of this project, it was not possible to design this device with other wearable forms in mind, and the application was designed with minimalism in mind to adequately meet the requirements of this project. The prospects of future work with this device are plentiful. The entire device can be easily downsized by implementing surface mount components and a single lithium polymer battery, allowing for a more aesthetic and robust design. Having the application run only on iOS is not ideal, and the software will need to be ported to an Android version to facilitate different users' devices. Additionally, the potential of multiple wristbands communicating to one central phone should be implemented to accommodate more diverse use cases. The user experience will also need to be
be improved for the application and the wristband, which can be tested through focus groups. Finally, the most significant improvement would be the use of Bluetooth 5.2, which brought the inclusion of angle of arrival and angle of departure technology to devices equipped with the chips. This new standard is up to 3 times more accurate, allows for sub 1 meter accuracy, and 5 degrees of direction error. This was omitted from this project due to the monetary constraints and should be investigated more in the future. From the team at Group 47, thank you very much for listening to our project, and I hope you enjoyed the video.